All right, welcome everyone to Deep Learning Adventures. Today we'll be going through the second week of our adventure into TensorFlow data and deployment. So for anyone who hasn't joined us before, just a little bit about the meetup. I'll share my screen here. So you probably found us on Deep Learning Adventures, meetup.com, Deep Learning Adventures. We have been at this for a little over a year. We started right after the beginning of the pandemic last year. Founded it. I'm lucky to be joined here tonight by my fellow organizers. The three of us began this together in April of 2020. And our first adventure was through a TensorFlow in Practice course. And since then, we've done a number of coding challenges. We've done a number of Kaggle courses. We've had some guest speakers. A variety of events on a roughly weekly cadence. Obviously they're all logged for posterity's sake here, as well as on our YouTube channel. If I can find the right here. There's many of our adventures. Everything that we've done, except for the happy hours, will be recorded on YouTube, so you can find them here on George's channel. Let's see, past events we already showed. So our mission throughout this whole thing has been learning, deep learning, and other related machine learning technologies, techniques, methods, working through papers together, and really just building a community of like-minded learners. We've been fortunate to not only work with the DC-based group that kicked it off, but we've had the opportunity to meet a lot of great people and like-minded individuals from around the world as a result of the pandemic forcing us all online. So a little bit of a silver lining there. Recent adventures, we finished the Kaggle adventure about a month ago, maybe a little over a month ago. And now, as you know, we are doing the TensorFlow data and deployments adventure. And you'll see we started it last week, May 5th, TensorFlow data and deployment. We did the first 2 weeks of the course. So this is the Coursera course here, device-based models with TensorFlow Lite, and that is next week's course that I'm trying to advertise here. Tonight we'll be doing the first course, the browser-based models, weeks 3 and 4. But before I introduce that, we'll talk a little bit about next week. We'll be doing device-based models with TensorFlow Lite. And this will be a really fun course. We'll kick it off with 1 week of considerations for different types of issues you may face when you want to move your models from the cloud or your local system into deployment on edge or even embedded devices. And then the following 3 weeks, 2, 3, and 4, will cover Android deployment, then iOS deployment, and then embedded system deployment. And looking forward to this. We're going to cover it kind of rapidly. We'll try to stick to the 2 weeks at a time pace. But there's a lot of material here and some really interesting stuff. And I know we have some people that are really interested to dive into this. So we may adjust that as necessary. But that's our current plan. So there's a visual here that I should show as well to attribute all the content that we will be presenting tonight to Coursera and Deep Learning AI, who have provided some of these educational tools and have really helped us educate ourselves and prepare ourselves to build projects and learn about the variety of things that one can do with TensorFlow. I also wanted to play a really short teaser from the introductory video for the week for the TensorFlow Lite devices. So we'll.
So I saw you building earlier today one of your robots with a screwdriver. This guy. So yeah, this is a sort of a self-driving car. It's built with a Raspberry Pi right here. So the Raspberry Pi runs TensorFlow Lite.
So that is apparently what we'll be up to by the end of that course.
Say no more. I'm sold. Where do I subscribe?
Therefore, we're doing the full size.
Full size? Let's start with small first. Guinea pig edition.
There you go.
All right, but before we get there, we would like to finish course 1 tonight. So to do that, I'm pleased to introduce my two great friends and co-organizers of this meetup. David Patton will be leading us through week 3 on saving Python-based models for use in browser inference and possibly pre-training as well. And then in week 4, we put it all together with using a pre-trained model and retraining the head of that model to play to recognize for rock paper scissors. So and George Zota will be leading us through that. Without further ado, I'll stop my share and we can get on to the main part of tonight's meetup.
Okay. Go ahead and share my desktop. All right. Okay, I assume you can see my screen okay?
Yes. Perfect.
Okay. So in week 3, as Robert said, we're going to talk some about using models that we didn't develop at the start of here, and then how to use some models that we didn't develop in the browser. In week 1 and week 2, we talked about how to build models and train them and then use them for inference all in the browser. But you're limited to the horsepower and the capacity that you have in the browser for doing the training. So it'd be nice to be able to do that training outside of the browser and then bring your trained model into the browser for actual use for inference. So we're going to go through that today. And luckily, we're going to get to do that with something that's not just an image model, which is new to us. We're going to actually do the first one that has to do with natural language processing. And then we'll do some image classification with a model called Mobilenet. And finally, we'll take our own model and train it in Python, and then use some really nice Tensorflow Js methods for converting that to JSON, which we can use in JavaScript inside a browser. So let's start with looking at some of the models that are out there already ready in TensorFlow for you to use. And I'll go through some of the code today that's in the week 3 part on GitHub. So if you haven't seen it, it's all available there. Even the exercises, although the answers aren't in there, but the full pages are there. If you're not familiar with the models that are available pre-trained in TensorFlow JS, they have some that you can use. Here's where they are, and there's an overview of some of them. There's ones for different types. The first set here are for working with images, either classification or different things such as segmentation and things like that. They have a model around speech. They've got a one for a couple for text. One that's these are very common things if you've seen Universal Sentence Encoder before. And then one we're going to use today, which is called text toxicity. And it's a model that goes through and given a sentence declares whether it's toxic or non-toxic and what type of toxicity is. And I'll show you some of that in a second. And then they even have a more general tool for doing K and N, K nearest neighbor classification. So those are just some ones that are available to you through TensorFlow JS. If they don't suit your needs, which they may not, you're free, of course, to develop your own models and use other models that are pre-trained in TensorFlow in Python, and then I'll show you later how to move those into JSON so you can use them. All right, so I'm going to show the code and go through it for the first thing. So I mentioned this toxicity model. It has a bunch of different kinds of toxic ways of classifying a sentence, and then it sums them up to decide whether it's toxic or not. It has an overall score. But we're going to go through how to use it here. And one of the first things we have to do is the first script line here is bringing in Tensorflow Js. And then the next one is where we're going back to that area where they have the different models and we're choosing toxicity. So here's the toxicity model that we're going to pull in. That imports the JSON and the weights and everything you need for your model to run in JavaScript. As I mentioned, this is pre-trained, so we don't have to worry about doing any training inside of our browser. One of the things that you do for toxicity is you get a score from 1 to 0. And if a certain, you can set a threshold so that if the score is above a certain level, you declare it as toxic. So you can play around with this in different sentences you provide the model and see how that works. But we'll start off by setting it at 0.9. I should stop for a second and just mention that feel free if anything's confusing or you have any questions or comments to chime in. I can't see the chat, but George and Robert are monitoring that. So if you feel more comfortable putting your questions there, that's great. But don't hesitate to ask questions. So the first way we're going to use this model is we're going to call the load function on it and give it our threshold. And that's going to go and pull everything it needs in. Basically, it's the same thing as almost like a compile where you're getting ready to use a pre-trained model in Python. This is how it's done here in the JavaScript. Call this load function, give it the threshold we're going to use. When that's completed, then we're going to send that model into this function, and we're going to call classify on that model with a list of sentences. In this case, we only have one sentence that we're putting in this list for testing here. And once classify completes, we're going to get predictions out of that we're going to log all the predictions, and we'll look at that in our console on the browser. And for each of the 8 types of toxic comments that you can have, we're going to see if any of them are matches and print out those probabilities. This all happens inside a script. There's nothing in the body of our page. You can put whatever you want here, but we don't need it. So let's go ahead and try to run that. So I'm going to go ahead and open that in a browser and take a look at it. Okay, so as I mentioned, there's nothing in the body, so this is a completely blank page. But if we look in the console for JavaScript, we can see that we have an array there that it printed out with each type of toxic comment that there could be. Everything from obscenity, it's explicit, it's a threat, and then the overall toxicity of the sentence. So every one of those is there. If we want to look at insult, for instance, you can see that this resulted in a probability, a match that was true, which means that it met our criteria for being over 0.9. The 0 is no, and it's binary here. So 0 is here, this is no, and this is yes, it was toxic, it was an insult. And you can see it's well over that. So you suck is obviously an insult.
David, do you mind zooming in
go
just
ahead.
a little bit? Sorry.
Go ahead.
Do you mind zooming in just a little bit so we can look at these numbers better?
Boy, I'll try.
Control plus.
Yeah, it's working. Okay, is that better?
Yes, thank you.
Okay. So let's look at to see if it's obscene and see what we get there. So here you can see the match is empty, and the probabilities we got 0.39 that it's not, and 0.6 was the yes, it's obscene. That's below our threshold, so that's why we didn't get a match here. So we've concluded, the model's concluded that this wasn't an obscene comment, but it came out as an insult. The overall toxicity is also going to be true, match of true. the probabilities are very strong that this was toxic. So, and then we if we didn't want to go and look at this, we printed out the things that were above 0.9. So here's the insult was found. As we said, this is an insult. The toxicity was quite high on it. We can do a slight change and test that out. Can you say you are kind? Surely that's not going to be an insult, right? Or toxic. And if we take a look at that, we'll reload our page over here. You can see, where is it? Is it toxic? Probabilities. You can see it toxic, it was matched as false, and it's very, very sure that it's not toxic, right? So almost 0.99. So that's kind of an idea of how we can use that. Does that make sense to everybody? I assume so. Let me know if you have any questions on that.
I found this interesting. Google also has like a live demo hosted on one of their websites. And I was playing around with it. I was playing with negation, you suck, you do not suck, you're cool.
Right.
Just the existence of the word suck makes it toxic. Like
it's pretty, yeah, it's not pretty good. It's not very sophisticated at figuring out.
Yeah. Negation doesn't work for me.
Right. If I put it, let's see, you are not kind. Let's just experiment really quick and just see what it says. Let's take a look at that.
Yeah, maybe. So it's not as extreme as it expects, I guess.
Yeah. So again, it's pretty sure that wasn't an insult when I said you're not kind. Maybe it wasn't harsh enough for it. I don't know. But yeah, so it's not that good. But you can improve it.
Yes.
All right.
So, David, it says maybe I'm missing something here. It looks like it's making 8 predictions, 0 through 7, but in the output it seems like there's only 7, 0 through 6. Just wondering if I'm missing something there.
Yeah, I'm not sure.
Should be
I
0.
think it's the same Python looping. Well, it's not Python, it's JavaScript, right? But it's 0 indexed and it's I less than 7, so 7.
Yeah, less than 7.
Oh, yeah, there's 7 of them. Okay.
Yeah,
Sorry. Not 8. Okay.
I misspoke if I said 8, sorry.
No worries.
All right. Okay, let's move on to the next example, which has to do with, make this a little bigger for you guys. Okay, so this has to do with using Mobilenet. And if you're not familiar with Mobilenet, it's a classification system. It's trained on, oh gosh, slipped my mind here, ImageNet. But it's built in particular to be small and efficient, very good for use on browsers and other small devices that you could use it with TensorFlow Lite. So Mobilenet is pretty common. I think there's multiple versions. This is one of the earlier ones, 1.0. So again, we're going to import the TensorFlow Js system and our pre-trained model, which is Mobilenet. This time we're going to have a little bit of content in the body of our HTML. We're going to have an image in there, an element with image. It's going to be a coffee cup. We're going to have an output div where we're going to write out what class Mobilenet thinks this is. And I believe Mobilenet has got about 1,000 different classes that it's trained on. And we'll see how it works for a coffee cup. Below that, we've got a script, JavaScript. We're gonna handle on that image element and that output element above. We're going to load Mobilenet just like we did with that toxicity model. We're going to call load on it. Once we get it loaded, we're going to use that model to do classification of that image that we've got a handle on. And then we're going to look at predictions of what the classification is for that image. We'll print those out as well as printing out any of them that we think this is going to be a fit for. So we'll print out the class name and the probability for it. Okay. So let's go ahead and run that. Any questions on this code? Does it make sense to everybody? Okay. So I'm going to load that in the browser and we'll see what happens. All right, there's our coffee cup. And it's running in the background. Let's look at the console. So it prints out the first 3 classes that it believes this is a fit for. You can see it's about 55% probability that it's the cup. Coffee mug, surprisingly, is lower, 0.2. And coffee pot. I guess maybe it was trained on something that looked, maybe it had a white coffee pot that it was trained on. It's pretty small percentage, but that's what it came up with.
It actually makes you wonder if there's some label error there as well, right? Like somebody might have just seen that, thought coffee, and clicked coffee pot instead of mug or something.
That's a good possibility. I think in ImageNet they do have some wrongly attributed images, and I know there's cleaner versions, and I suspect that this Mobilenet was probably trained on the original version, not the cleaned up one.
But I also don't know. It could be that there are no other classes that are that much closer to the first 2.
Yeah, certainly could be.
It's low probability.
Anyway. So this was a neat way of showing you how you can actually use elements on the page. You can imagine uploading instead of just hard coding an image in here, that you could do an upload field. On completion of the upload, then you could go and classify it. So you could do this in a live format kind of experiment. So you can see kind of we're building up that capability to do that kind of thing, and we'll see that later on with George. So those are kind of ideas of how to use these pre-trained models that are available as part of Tensorflow JS. But what if you want to build your own model and train it and then pull it into your browser for doing inference, or let your users pull it in on your web pages to do this? But you don't want to use the limited capability of a single browser doing this training. You want to take full advantage of, and it's possible you may have a huge amount of data that you're going to train on, and it's just a lot easier to do this on the server side with powerful TPUs or whatever you want to do it with. So the next thing they're going to talk about is how to do this with your own model. So we're going to look here at a notebook called Linear to JavaScript, and they're just going to do the same model that basically George introduced in the beginning, which is just training a linear model that's on a function that's 2 times x minus 1. So if you remember, it's like 2 times minus 1 is minus 2, minus 1 again is minus 3, and then 2 times 0 is 0, minus 1. So in this case, George, I noticed he actually had this right. I think before we had a 2 there.
Yeah.
Yeah. So in this case, they actually got the array right. But anyway, so here's what's kind of going on. We've got a Jupyter notebook here. The first thing we need to do is install Tensorflow Js, because in Collab I don't have Tensorflow Js by default. So we're going to use pip to install that. Then we're going to run import NumPy and TensorFlow that we need. We're going to create a model, and this is just a straight linear model. So we have a sequential model with a single dense layer with just one unit for that, that W for the WX. The input shape is just a single value coming in. We're going to compile that with stochastic gradient descent. We're going to do mean squared error on our loss function. And we're going to use this as our training data. We're going to hard code that in here. And we're going to do a fit. So this is just like we've done in many different Jupyter notebooks. We're going to do this for 500 epochs. It trains very quickly. And once we get to the bottom here, I'll just scroll down. So once we get to the bottom, we're just going to test it with 10. So 2 times 10 is 20 minus 1. We should be close to 19, which we are. We're very close. And here's the new thing. So we're going to first get a import time. We're going to use this when we save our model out. We're going to have a path that we're going to define as the current directory times the formatted time that we're going to put in there with a .h5 ending. And this is a typical TensorFlow way of saving a model. We're going to call model.save to save it out to this path that we've created. And it'll save it in our local files over here. And then we're going to use a nice little utility from that library that we had to do the import on above and install. The Tensorflow Js has a converter in there. You're going to have an input format of this Keras saved model that's telling it to use this way of formatting. And we're going to give it the path to our saved model over here. And what that's going to do is it's going to give us a JSON format of our model. When we did save model here, it's this H5 model, which is a different way of saving a Keras model. Here we're going to produce a JSON file and what's called a bin, which has your weights and biases and things. And I'll just go ahead and run the whole thing just so we can see it in action. Like I said, it's going to run really fast. Here goes the training. Should finish a second. It's probably finished.
I notice Colab now gives you the actual function being called at the very bottom.
At the bottom, yeah. So it's completed running, and if we refresh our files over here, we can see this is that model that we saved with this time format to it for the naming convention, just so we get a unique name for it. And when we call this step, it produces this model.json and this group of shards of binary files here that has the data we need to format our model for inference. You may get, for a large model, you may get a lot of this. This is shard 1 of 1. If you notice, you might get shard 2 of 10, or get a whole bunch of them. So very large models, you get more than this. You're going to use these in your browser, so you don't want to have too large of files that you're importing in and pulling in. It's more efficient to have smaller ones. Takes less memory. So to deploy this, you need to copy this into the same area, or at least have a reference to it inside of your browser, inside the HTML, the scripts where we're going to call this. Just like we called for like Mobilenet, we had to call it from the TensorFlow site. Here we're going to call wherever we've got this this being hosted at, so on a web server somewhere. So I'm going to go and look now at how he does it in the class. He's running a web server. I'm running a web server on my local server. And in here, I have an HTML called linear.html, and I'll show that in just a second. And here I've already downloaded my model and my group shard 1 of 1 bin here. So all my files are in the same directory. And let me show you the linear HTML page so we can see kind of what's going on there. So here, I think this is it. So here it is, and it's, again, there's nothing really in the body, but we have a script, and we're going to have an asynchronous function. We talked about these before, but notice above that I imported TensorFlow JS, but nothing else, right? So I'm going to set a URL for where my model is being hosted. This could be a HTTP link also, not just a local, but in this case, I've got them in the same place. I'm going to load that model with this command here, tf.js. load layers model, and I give it the URL to where this is. It could be anywhere on the web that I'm allowed to get it from. I'm going to print out the model summary so we can see it. Remember, it's a very simple model. It's just that linear model. I'm going to test this by creating a that same test I did when I was doing training, where I'm going to put in 10 and hope to get something close to 19 back when I call predict, and I'll alert on that and we can see it. I need to call this command after I've defined it, and we'll watch it run. So let's go ahead and do it the way he's done it here, which is on this web server that's running locally. So if we load this up, all right, so it's gonna run and show. Here's my value that we saw pretty much before. We can look in the developer mode if we want here. We won't see really anything here. Here's the model that we built over in Python on Collab. Remember, it was just a single dense layer. It only had one weight in there, or one parameter, plus a bias. So we have 2 parameters total that we're looking at. And so that's how this functions. Any questions on this before? I'm going to show an alternate way of doing it, but
David, can you just review that that one file that you pulled in, the bin file? I was a little confused what you were saying there.
Sure. So when you save the model out, it saves the model architecture and definition as a JSON file, but the trained weights and biases that you've completed training are saved in that bin file.
Mm-hmm. Okay.
And it's used for initialization of the, when you pull a model in, you want to pull it in that way so that you can, behind the scenes, basically it does a compile of it to get it ready for running.
Thank you.
Does that make sense?
I think so, yeah.
Okay.
David, just curious. So, how large is the model? Is
How
the
large
file?
is it? Yeah, that's a good question. Let me go back to the. I think I have what I have. Look here, actually. Not here, maybe the other one. Here we go. All right, so this is the model that I trained. It's only about 1K, and here's those 2 parameters. The weight bytes are very small, 8 bytes.
That's a model.json should be human readable, right?
The JSON is, yeah, we can open that.
Yep.
Let me open that for you.
And generally speaking, David, do they discuss like any guidelines or rules of thumb, like how the maximum size of the model to be sort of qualified to be mobile or like portable to devices, etc. Is there like a?
They don't give an overview during the course. I think there must be some of that in the documentation, because you're right. If it's too big, it's going to be very, very slow in the browser. And the other thing I ran into is the model has to be Keras based. In other words, Keras layers, right? Those kind of things. Keras optimizers. Well, the optimizer doesn't matter if you're training. If you're not training in the browser, the optimizer doesn't matter. But your layers have to be Keras based models. I found that some of the more advanced, I tried a few more advanced things, such as some of the augmentation things and inside my model. And when I tried to do inference in the browser, it said, "Oh, it's not supported by TensorFlow JS." So
Okay.
that was a got you that I hit. Yeah.
Using the same type of augmentation that we did in the convolutional course.
A little different because I was using the layers. So there's some Keras pre-processing layers that you can use. So I was trying to do it there, but it didn't work.
I was curious, this model.json, does it tell us I mean, it looks like it has some metadata in it as well. Does it tell us what loss and optimizer were used?
Let's see. Yeah.
Just printing it all in one line makes it a little.
Yeah, unfortunately here, let's
You can use you can
Class
go to like a
sequential.
JS beautifier. That's what I usually do, and just paste it there.
Yeah, I was trying to see. I don't. It's telling me about the model.
Got the layers of your network.
Yeah, it's telling me the model architecture.
It's the
region.
model architecture, yeah.
Everything that we've seen so far.
I don't see anything
Lots
telling.
of
Oh,
there.
here it is. Yeah, here it is. It's also the train config, so we know at least
Ah,
what the loss that was used.
So it probably
Tell
has
me anything about the optimizer. Here's the optimizer config.
SGD. Yep.
there it is.
and it even tells us how it was.
Learning rate.
too.
Yeah, even the
Tells us
default
what
parameters.
What the
Very cool.
initialization procedure was, at least.
Who knew?
So the funny thing is, if you put this out on the web, you know, you're opening up everything about your model is going to be viewable.
Well, the weights are in the bin file, right?
Yeah, you won't have that. I mean, they can always just snag your bin file. But
Well, you need the data.
yeah.
Is it just those two files that you need then to pull over into JavaScript? You just need the dot bin file, which is the shard file, and then this JSON file, the model, and the other stuff you don't need, like the H5. You don't need anything else from.
Yeah, and I'm going to show you something about that in a second. But yeah, you only need the JSON file that has your all of this information in it, and the shard, and there may be multiple shards.
Right.
So as long as you have that's all you need, and they have to be in the same place. When I say that, I mean served from the same place. So if you have them on a server or local, whatever. Okay. All right. So
If we only have two parameters, we can fit them all in one shard at least.
Yes, very easily. So if you recall here, he went ahead and built his model, did the training with Python, and then wrote out the JSON and the bin file by first saving the model in a Keras format as a .h5, and then using a utility in Tensorflow Js to build that. So there's an alternative way. You can do this all in Python on your local device or any other device. You don't need to use a notebook. And I just wanted to show that real quick. So in this case, you can just import, if you already have this installed, pip, you can import it with tf.js in a straight Python file, right? I'm importing tf.js. Same thing as before that we did before. Here's my model. Here's my training of that model. And here, instead of doing all this, saving the model out to a file, you can still do this if you wanted to have it. You can just call straight from tf.js. You can just call this converter save Keras model, give it your model, and then a path where you want to save it. And this will create your example. So I did this, for instance, in a separate directory called DLA for us. And here you can see I just ran this Python, which you see on the right, and it produced my model.json linear. And I'll go ahead and show that here. Whoops, sorry. I'll just open this one in my browser. And there it is, same result, right? Same thing happened, it worked perfectly. So if I view the console, nothing here. You can see the model output. So there's the same output we saw before. So I just wanted to show that as an alternative, that you don't have to use Jupyter notebooks and you don't have to use the utility they were using to convert. That you can do it straight from Python.
Nice.
Yep. So that wasn't in the course, but I thought people might find that interesting. So the last thing in the course is going to be, we did ImageNet for classifying. We did the linear model here on how to convert your own model into JSON format. And then there's an exercise where you're going to do essentially some of this, and it's a very straightforward. I think you only have to do two things in the actual exercise. So I'm not going to go through that much. I didn't think there was much value in presenting that, but I wanted to do a little bit of a dive into something different, which is to show how you could use this. So what I did was I created this thing called Deep Weeds, sorry. So this would be appropriate for this deep learning. Deep Weeds is an image classification data set that's available through Tensorflow's dataset catalog. If you have any questions about it, you can go get it. But it's over 17,000 images, and it was images taken in Australia of I think if I recall, there's 8 different kinds of weeds, plus pictures of what they call negative, which is ones that don't have any of these 8 weeds in them. So these is in Queensland, weeds infestations. It's all one data set. And here's an example of what some of those pictures look like and some of the different labels. They're actually labeled with numbers, but this is kind of what they reflect, lantana, snakeweed. And here's some of those negatives that don't have any of those particular type of weeds in the images. So you've got a large number. And so I took this data set and built basically, I'll show you, I did it in Collab because it's a pretty large data set. So let me get over to that real quickly. So I built my own model with a CNN. Again, you have to pull in the data set, but again, I'm just pulling in Tensorflow Js for what I'll do at the end to get the model JSON in my thing. So it's a very straightforward data set. I'm going to pull the data set from TensorFlow's data sets. For simplicity, I'm just going to pull out the images and labels and put them into some NumPy arrays, X and Y. I'm going to break up this data set into a train and test set of data set. It's slightly imbalanced, but not, I'll deal with that in a second, but I'm going to stratify on the Y, which means I want my distribution of these Ys or these labels to be the same form of distribution in my train and test data sets. I'm going to save 20% for testing, and the rest I'm going to use for training. You can see here's the shape that I'm getting for my training set for the images. They're 256 by 256, and they're in color. And I need to balance the data set. So I just use a simple random undersampler to take the majority and balance it with the minority classes. There's some tricks I had to do to use images, but you can see before, this is the negatives. The 8 were the ones that have no weeds in them. They're much larger than the other ones, but there's still a good number of the other ones. But once I do this resampling, everybody has the same. So my classes are all balanced, right? Before I tried using class weights and didn't have a lot of luck, so I went with this actual resampling method to do it. Here's my model. It's a pretty basic model. It's just going to have an input shape that I talked about for the images. And then I'm going to use some convolution or layers and max pooling to do this. I'm going to flatten it out at the end. I use dropout because there's some overfitting here. There's quite a bit of overfitting actually. And I've got these 9 classes that I'm going to try to predict with a softmax. So I'm doing a classification problem here. So here's a look at my model. It's pretty small. It's not huge, but it's a lot bigger than that 2-parameter one we were looking at before. It's not the greatest model, as you'll see. I'm going to compile and use Atom. Since it's just single integers, it's sparse categorical cross entropy. Pretty typical things we do here where we fit it. I'm going to stop early, so I'm not going to go 300 epochs if it's not improving. And it turns out it goes for, I won't run this because it takes a little while, but it goes about 61 epochs. And I saved back here in my early stopping, I saved my best weights from the model that had the best validation accuracy. Again, nothing sophisticated here. I didn't do anything to really make this a lot more accurate. Here's a look at the training. It definitely has the overfitting going on. And when I evaluated on the test set, it only got, you know, about 58% accuracy. But if I looked at what if I was only choosing the negatives in my test set, if I just chose these guys, you know, it would be about 52%. So it didn't learn to just choose the majority class. It actually, that resampling I did helped it learn when to choose some of the minority classes. So it's doing better than just choosing the majority class, and it's doing a lot better than just randomly guessing. So it did learn a little bit. It's not great. And then, as I showed before, the simple method for saving this out is the tf.js converters save the model, and I'm just saving it to my local set. So any questions on the training of this model?
This was cool, David. Thank you for sharing with us. What is this counter-wide test? Is that just giving you a distribution of the labels in the test data set?
Which one?
The
Yeah, I just wanted to show the test data set that it was also imbalanced, and if it had, I did this so I could do this calculation right here. I needed to print it out. I went back and put it in to see what it'd be.
Got it. But you
I just wanted to, when I didn't train with the sampling, the model would learn to choose 8 because it could get about 60 something percent, or no, it could get this 52% accuracy all the time, and so that's what it would do.
Got it.
You know, it's very common for an imbalanced data set for a model to learn the majority class, to predict the majority class all the time.
Yeah.
It can score pretty high. Yeah.
But you trained it on a balanced data set, right?
I balanced my training set, only the training set.
Perfect.
So that I could get better results.
And you said there were some tricks there since you're dealing with images. What did you mean by that?
I'll be happy to share this later, but yeah, it's a simple thing. So this, I used there's a library called IMB Learn. You know, it's kind of a play on sklearn, called IMB Learn. And when you call with your sampler, when you try to actually fit and resample this, it expects to have a single dimension array here and your labels. And so when you call, you know, when you have you'll have this plus a whole, you know, 256 comma 256 comma whatever. It's going to say you've got 4 dimensions when they expected only 2. So what you have to do for images is reshape them by just, you know, basically making this 1407 by whatever this number is times itself, right? But then after you do your resampling, you're going to get back something that you now need to reshape it back into the image format that your model is going to expect.
Got it.
So that's just a little trick to be able to use this library. And there's much more. Sorry, I shouldn't say. There's a lot more sophisticated samplers in here than just random sampler. This is like the most basic one. So there's some that'll look at nearest neighbors. There's some that'll do both oversampling and undersampling. So I think we may have seen that in some of our other courses. But
David, and how many weights? 83,000, right?
For what was that?
How many weights? How many parameters in the model?
Oh yeah, 475.
Oh.
So it's not that big of a model.
Mm-hmm.
It's not that big, and it's you know, but I wasn't trying to do the best. I just wanted to use this as an example. So now in my
it was already overfitting, right? At some point.
It was, and that's why I did the early stopping to prevent it from overfitting too much.
So I guess you know, one might ask a question like, did you have to sacrifice anything to be able to squeeze it into light version as opposed to, you know, full-fledged? If we have, you know, if we didn't have any of those limitations.
Yeah, that's the thing, is I don't know what. There's probably a guideline for browsers. You can probably throw any size at a browser, but you know, eventually you're going to run out of memory. So I don't know, as far as the model and the bin files, if there's any. There probably is best best recommendations of how to best practice for this, but I'd have to go back and look through the TensorFlow JS documentation to figure that out. I mentioned real quick that things like random rotation, some of the things you might use to improve, I couldn't do it inside the model. You could instead of doing it the way I did it, you could use image data generators to feed your training data and do it there. So I could have done things like that to improve this. I was just trying some quick ways, but
Oh, you mean, sorry, you mean you couldn't do it?
the reason I couldn't do this is because this now becomes part of my model architecture.
Oh, I see.
And when you try to deploy this out onto the browser, TensorFlow JS will say, I don't support these. They're not there. So not all of the Keras, this is experimental, right? So these aren't available yet in TensorFlow JS.
Got it.
If you stick to the standard Keras layers, you should be good to go. I had no problem with that. So
Good to know.
all right, so the outcome of this, my files are gone, but the outcome of this was that I got a model plus my model.json files plus my bin files. And we'll go back and look in my deep woods directory here. Here is my model.json file. Again, it wasn't that large. Let's look in my directory here. Let's look in deep woods. So here, my model is a little bigger. It's 7 instead of 1. And I've got 1.9 megabytes, whereas before my shard was only 8 bytes, right? So it's increased quite a bit. But I do know there later we're going to see some, I think George is going to show us some where we're going to get multiple bins.
Yeah.
Yeah, multiple shards, as they say. Sorry, one bin with multiple shards. All right, so how am I going to use this now? So I created a weeds.html. It's like most of the others. You're going to pull in JavaScript. I actually have a secondary script I wrote called weeds.js, and I'll demo what's in there in a second. But in this body of this, all I'm going to have is a few test images. I give them a unique ID and a button under each image that calls a classify method in my script and passes in the image button and the ID of the image for me to do the classification. So let's see what goes on in the JavaScript. And let's make it bigger just for everybody. Sorry, keep forgetting about that. So the first thing I do is I have them, and I'm not a JavaScript expert, so this did take me a while to figure out, and there may be some errors here. So, but I found that I needed to have a model declared, an object declared up here. First thing I'm going to do at the end of this script is I'm going to wait for the whole DOM to load, and then I'm going to call the run method, which is an asynchronous method. Basically, it calls get model, waits for the model to be loaded, and prints out the summary. Here's where I do that get model. It's very similar to what we saw before, where we call tf load layers and model JSON, and it just returns the model down to run here for us to use. When we press the button on the page, this function is called classify, and in there, if you recall, I was passing the ID of the image that button is underneath. I have some debugging still in the code, but it's going to print out that image ID just to show that I got it. Here, I'm going to use a get element by ID on the document with the passed in image ID to get that raw image. I'm going to print out the source around that to show which one I got. And then I use a function in tf.js called browser.fromPixels. It converts that raw image into pixels. I need to resize it because the example images I have are smaller than this, so it's actually maybe not going to be as good because they don't match, because I pulled them from the samples, but they weren't the same size, so a different page. But I'm going to resize them to the size I need. The other thing that's important here is when I'm calling raw pixels, I need to remember that I've got 3 color channels. And if this was black and white, I would just use that black and white as 1. Here, I just expand the dimensions, make a tensor out of this resized data, and I call model.predict on that tensor, which gives me a prediction back. And I can also get which ones got the maximum value, so I can print out the actual value. So I'll print out that that alert. So that's what happens in the script. Any questions on that? So let's try it. Let's load up weeds.xml. Remember, it's using my model that I trained over on Collab, and I pulled down the JSON, everything I need locally. So let's take a look at that in the browser. And this was not in the class. I just wanted to show kind of how this could be used on a much larger model and data, and why you might want to do this in Python and not in your browser. Remember, I didn't point it out, but I trained this with like the GPUs on Collab, and they're much faster than anything I could do with my browser and the CPU. So, all right, so here's the page. Let's open up the console so we can watch any messages. All right, so here we see that model again that I created over in Python with our different layers and everything, and the full number of parameters. And let's see what happens when we try to classify this one. So this is image number 1. I labeled it as I1. Here's the image URL that it's pulling, the source of the image, and this is called Chinese apple, or 0. Just remember the label is going to be this number. So this is number 0. Now let's see what it does when it tries to predict. It got it right. So it got a 0 for this one. So that's pretty good.
Nice.
So the model didn't guess that it was a negative, that it was 8. It actually guessed it, got it correct. So maybe it's not as bad as I thought. This one is I2. This one is a lantana, which is 1. So let's see how it does on that. Well, didn't get that one right. So this one, it guessed it was a 7. It didn't guess negative, but it guessed it was one of the other weeds. I think this is a pretty hard problem for image classification. So let's see, I3 this is a negative. There's no weed here, believe it or not, or at least not the 7 weeds or 8 weeds, sorry, they were looking for. It got it wrong. It thinks there is a weed there. It thinks, in fact, I think that was lantana.
I think there's a weed in there, but I don't know.
Well, it thinks it's this, though. It thinks it's this weed. So.
Oh, I see.
So it didn't do so well there. And the last one here is a funny named one, I think. Yeah, snakeweed, and it's a 7. Let's see how it does on snakeweed. It gets snakeweed right. So it actually thought that this one up here, which I think is Chinese apple, was the same as that. And you can see the similarity. They're pretty similar. So with my naked eye, I don't think I could tell the difference.
They're actually different, right?
Yeah, this is
0.
Again, this is 0. It's Chinese apple.
Yeah.
So it got it right, and it actually got the 2 that I would have thought it would blow up on, and miss these 2. But who knows?
Interesting.
All right. I welcome questions. Anything in the chat?
I think most people have been speaking up when they have questions, so we don't have anything outstanding there.
Okay, excellent.
And I'm looking forward to deploying this on the phone, so I can go into deep in the weeds and find some weeds and classify them for you, David.
Yeah, you just need to run to Queensland,
Queensland,
Australia. although there may be here too. I don't know.
Of course.
I know they did this in Queensland, so they could be here also.
There's a lot of AI startups that are doing this image classification of weeds, and they're spraying pesticides. And I saw in the news there's a better approach where there's a huge farmer robot that looks at images of plants and weeds and uses lasers to just eliminate weeds instead of using spray for.
So no chemicals. I like that.
Yeah. So it was like this flashing robot. I was like, what in the world?
That's pretty cool. Yeah. I'm interested, Dimitri, hopefully we'll look up that you saw this was pretty fast in my browser. It's not that big, I guess. But it'd be interesting to see what the recommendations are for maximum size of your model and your shards for the .bin files. Yeah. All right, I'll turn it over to George for week 4.
Thank you. Thank you. Thank you, David. I'll take a quick break here, commercial break. I'm gonna give some letters to my guinea pigs here for everybody watching online. These are my guinea pigs here. Hi, girls. Say hi to our friends. And this is not a wig. This is just letters. Hi. Come here. Come here. Come here. There you go. There you go. You get half, and you get half. I wanted to do something with, I plan on doing something with my guinea pigs in one of my adventures. So we'll see how that goes. Cool. Thank you, David. That was really interesting. Thank you for taking your own path and exploring that data set. That was very interesting to me. Awesome. So for week 4, really week 3 was really content packed. And after going through week 3, I felt week 4 was a little bit easier to go through. I mean, it had a lot of information in it, but after going through the first 3 weeks, I think week 4 was a culmination of everything that we learned. So what we're going to look at week 4 is we will actually use a pre-trained model, Mobilenet, like we've seen before with a coffee mug. And we'll actually use that as our first model. On top of that, we're going to build our own model, and we'll do an end-to-end classification using this combined model. We're going to work with the webcam, which is also a super fun adventure. We're going to capture images live from our web feed, and we're going to convert them to tensors, and we're going to have a fun experiment with recognizing rock, papers, and scissors, which reminds us a lot of the teachable machine adventure we had way in the past. And if you're joining us, if you don't remember that, if you Google on YouTube, Deep Learning Adventures, Teachable Machine, we had a fun session with that. Cool. Let me start with, I want to start a little bit with Mobilenet. So Mobilenet has been around for a while, and has multiple layers. It was actually, as you know, it was designed to operate well in low power, low memory setups. And what we're going to do is we're going to take an original Mobilenet model that's trained on ImageNet on 1,000 classes, and we're going to further train it. We're going to freeze some layers up to a point, and we're going to drop the, let's say we take this from top to bottom. We're going to take probably the 80% of the layers. We're going to drop the 20% of them, and we're going to use that as our basically feature detection or feature generation. And on top of that, we're going to add our own model to do our own classification. So the code for Mobilenet is also available online. You can look at it. It has this deploy convolutional blocks, and we're going to look at how do we plug ourselves into this layer or this collection of layers, and how do we pick an output from any layer here. And just to give an idea of Mobilenet, how has it been performing on papers with code. Here you can see image classification on ImageNet all the way from 2011. And I think Mobilenet is somewhere, yep, somewhere here, 2017. Yeah, about 70% accuracy. And if I look at, let's see what other versions of it are there. So V3 actually received what, 79%, yep, back in 2020. 75, 75, 74. And so you see the progression. Maybe I should have done this in reverse. Yeah, let's do it in reverse. So the first time it appeared was what, 64%, 2019. DY Mobilenet V2, 69, 69, 72, 72, 74, 75, 75, 2019, and now it's 79, 2020. I wonder where it is. Somewhere here in this stack of, somewhere here, yeah. ResNet, student. Cool. All right. So for our application, I want to start a little bit with how do we interact with the camera. I think that's the first new thing that we're going to see here. Let me zoom a little bit more for us. So we're going to use this webcam.js. I'm not going to go into all the details, but I just wanted to show us how to interact with the camera. So we have basically a capture method here that it will use this tf browser method from pixels, and basically it will look at a webcam element. We'll see that in our HTML page we'll have a webcam element. It will grab that element. It will convert it. So here's the image as a tensor from the webcam. So we'll convert it to a tensor, and it will do some basic pre-processing, like cropping it maybe to a specific rectangular input, maybe expanding it so that it's just one large vector, and normalizing it between -1 and 1. So here we're dividing by 127 and subtracting 1. Yeah, cropping is there, some video size as well, some setup. We don't have to know this. It's just I thought it was interesting to see the new element in our adventure here. Cool. Then for our main page, we're going to use again tf.js as we've seen in the past. We'll use that webcam.js that we just saw, and we'll use this rock paper scissors dataset.js. So I'm going to look at it in a moment. And for our body, we're going to have a div containing a video element, width, height. We're going to name it as webcam WC. And then we're going to have a few buttons here. We're going to have a button called ID 0 that will have a label called rock, another one called paper, another one called scissors, and as well as a place for us to write information to, so rock, paper, scissors. We'll have another button for training the network, do training, we'll call this method, and another one for starting the prediction and stopping the prediction. So before we go into the code, let me actually show the demo of how this works, and then we'll take a closer look into the code. So I'm running this web server for Chrome that we've been running through our adventures in this course. And this is week 4 examples retrain. Sorry, I didn't want to do that. I just want to click on it. There you go. Week 4 examples retrain HTML. And let me open the console. And zoom in a little bit. Zoom in here as well. There you go. Oops, sorry. Make this a little bit smaller. Awesome. So there's a lot going on here. I don't want to focus on the console. I want to focus here. So actually, let's look at the code instead. So this is the video element that I was talking about. As you can see here in the code, we have our buttons, the rock, paper, scissors. We have some place for us to write information to, how many samples we're capturing for each class. We have a button for train network, some text, and then a button for start predicting and stop predicting. Cool. So what I will do is I will train this Mobilenet network. I'm going to see how it's structured in a moment, but I wanted to show the demo just to get us a little bit excited. So I'm going to hold my hand close to the camera, and I'm going to click when I click rock, it will take a few samples from me. So I'm going to do maybe 20 or 30. Let's do 30. Let's do paper. Paper, about 30 of them. And let's do scissors, right? Let's go like that. Let's do 30 of them as well. So now I have about 30 samples of each class. And we're going to look at an example into the code, what exactly happens behind the scene. But really what we did right now was basically capture our training data. So I'm gonna click on train network. It'll train it for us. You'll see the loss is decreasing. And once the loss is not updating anymore, I can do start predicting. So start predicting, it's actually capturing live image from my camera. So let's see, rock. Depending on where the rock is, might think it's a paper. This is definitely a paper. Let's see if I can break the paper. No. And let's do scissors. 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 Maybe I didn't train it well. There you go. So the distance is important. If I come closer, it'll think it's something else. And also rock and paper was not that easy to distinguish. So you saw it's just 100 training samples. I was able to build like not so great classifier, but if I maybe capture more data and a little bit more consistent with my position of my hand, maybe I got a better performance. Okay, I'll stop predicting here. Cool. So let's see how this works under the hood, right? We saw how this works live. Now this HTML makes a little bit more sense. And let's look at this red rock, paper, scissors dataset.js. This is a class that we're going to use in our index.js file. We'll use this to capture our data, and our data will basically be captured in the X's and the labels. So in the beginning, when we start this whole process, the labels will be empty, and empty list or array labels. We're going to call this this method called add examples that has an example and a label. If this is the first time that or the first capture that we do, we will keep that image. And tf_keep and tf_tidy are, think of them as antonyms. tf_tidy will delete any tensors in Tensorflow JS that is not currently used. tf_keep will actually keep them in memory. So we want to keep that in memory, and we actually want to append this in our label, in our labels array. Otherwise, we're going to do is, I think this is just like JS syntax in Python, right? You can have left-hand side and right-hand side to be the same. But here we have to use an intermediate variable called oldx, which is our existing images. And this points to the data set of our existing images. So we take the images, we store it in this variable oldx. We concatenate that with the current example. We also append our existing label, and we get rid of the oldx just to save some memory in tf.js. Another class we're going to use is this encode labels. They just saw my IDs were 0, 1, and 2. We actually want to one-hot encode them, and we do that in the very end. Once we collect all the labels, let's say 100 labels for all the 100 images, we're going to go through all of them, and through each one of them, we're going to call this tf1hot with the current label. And depending on how many classes we have 3 classes for now: rock, paper, scissors. Cool. Really, this is the main classes here. Let me zoom a little bit more. So let Mobilenet model our variables that are used.
George, can I ask you to go back to the prior one?
Yep.
So if I remember right, it looks like down in the encoded labels. You know, when I first looked at add example, I thought, well, it's weird they don't do tf_keep on the labels, right? They only do it on the images, right?
Mm-hmm.
But down in here, it's actually when they do that one-hot coding, they want to keep that result, but anything that gets them to there, they do tidy, right? Is that your understanding?
So
this is very, JavaScript, but it's actually part of tf.js. So
yeah. This combo is new to me as well. This keep and tidy at the same time. Usually you do tidy when you're doing intermediate calculations and you don't want to keep any results unless that is returned by a method. So in this case, I think it's good to do tidy, but keep with tidy, it's new to me as well. I'm not sure what is the combined effect of this.
I don't know if anybody else has any knowledge of this, but my understanding or my interpretation of it, I don't know for sure is that it's keeping the one hot version of the labels in memory, but the other, just straight labels array that it created up in the constructor, it's cleaning up those values up or something. I don't know. But that's sort of my understanding.
That makes sense.
So it's keeping the result of that function it's defining right there, while not keeping the function definition itself.
Right. Okay.
Is that it?
But it must.
I was very confused by that as
Yeah.
well, but I didn't try to spend too much time learning it.
It must clean up the labels too, because back in the add example, it didn't put the TF keep on those. I thought that was right. Or maybe it doesn't.
Is that because you're actually defining them though? Here
Could be.
as an array. So
Yeah, it could be because you're putting them in that list up there. I'm not
so
sure.
yeah, so that's a predefined list.
Maybe that's
The other
what.
thing I thought was interesting was that the constructor reserves a space for the labels, but not the x's.
Because the x's, you don't know how big. I mean, no, you don't know how big the labels are going to be either. Yeah, I don't know. It's a good one.
Have you used, guys, tf keep outside of JavaScript?
No, this tf tied and tf keep are specific to
Specifically for
JS.
JS? Okay.
JS, yeah.
All right. Well,
Cool.
it's a mystery.
Yeah, we can look it up. So yeah, we're going to use this Mobilenet. Let's define some variables, and model will be our model. We'll go back to our HTML page and grab that webcam element. That's our webcam pointer. And we'll create this dataset constructor from this dataset.js. We'll have some variables for rock, paper, scissors, initially 0. And then based if we're in prediction mode or inference mode or not, initially this will be false. Cool. We have an asynchronous method here to load Mobilenet, and we do that through a neat way actually with this tf.loadLayers model, and we just point it to a JSON file. That JSON file is on tf.js's API, right? We don't even have to have it locally anywhere. So that's the Mobilenet v1 0.25 Mobilenet version. I'll print it out here for us so we can see how it looks. And then I will actually grab a specific layer. So while I do this, let's look at Mobilenet. So this is the mobilenet.summary. So input layer 224 to 24 by 3 and number of batches here. Conv, batch normalization activation, conv2d, batch normalization activation. We'll go back all the way to conv pw 13. 11, 12, 13. So that's 12 right here. Conf pw13 relu. So this is the layer that I'm interested in. This is the one that I'm getting the output of my Mobilenet. See, after that, there's a few more. There's a global average, there's a reshape, a dropout, a conv2d, and then an activation and a reshape. So I'm actually interested in the last, maybe conv, or maybe second to last, before the output of the final output of Mobilenet. So I'll grab that layer. That's my pointer to that layer, and I'll actually create a new tf.js model with inputs will be whatever inputs Mobilenet takes to 24 by 3, and the outputs will be that specific layer's output. So that will do basically uploading or recreating my model. Let's actually start at the very bottom. So we have an idea of how this works. So init, this is what this page will run, and init will do the setup of the camera. It will load the Mobilenet, and after that, it will capture an image from our webcam, and it will call predict on our model, and that's what we're going to see. Let's look at the other buttons that we have, right? We have a training and a start predicting and stop predicting. When we call do training, we're going to look at a method called train. When we do start predicting, we're going to set this variable to is predicting true, this binary variable. And when we I'm going to call this method called predict. So let's look at training a little bit and inference later as well. So training, we're going to create this data set from scratch. The Ys are not, we don't have any Ys yet. So this is called after we get the data actually. So when we do this encode labels that we saw here, this will actually, we have access to all our labels, and this will actually convert them to one-hot encoded versions of them. Our model will be the output of Mobilenet, the very last output. We will add 2 dense layers on top of it. We'll add a dense layer with 100 units and rel activation function, as well as a dense layer with 3 units because we're only classifying 3 classes here, rock, paper, scissors. So basically what we're doing here is we're taking the output of Mobilenet from that layer 13, and we're adding our own DNN on top of it. We'll train it with Atom Optimizer, categorical cross-entropy, this one hot encoded, loss variable, and then we're going to call model.fit. We have our images here that we added, if you remember from here, and our labels, one hot encoded. You can train this, let's say, for 10 epochs. And in the meantime, on each batch end, we're going to plot the loss. Awesome. So that's the training part. Let's look at the prediction part. So the prediction part will look at this variable, if this is true or not. If we are actually predicting, we'll capture an image from our webcam. We'll run it through our Mobilenet. We're going to get our feature activations, our feature set. Then we'll pass that through our own model, model.predict, and we're going to get our predictions. And then we'll convert that to one output. We're going to take the max out of 3 numbers. Then based on what this number is, if this is 0 or 1 or a 2, or based on the location in the array, if it's a 0, 1, or 2, we'll classify it as rock, paper, or scissors. We'll also insert some text in our HTML page. And then some cleaning up here. This is just a tf.js. Cool, so that's the predict method. The last one that I didn't cover.
Random JavaScript question.
Go for it.
That line 69 there with the predicted class dot data with the 0th element on the end.
Mm-hmm.
I don't think we saw that data element anywhere else. I was wondering if anyone knew where that came from.
So yeah, so this is the result of this tf tidy capturing, predicting, picking the max, and storing it as a single array, one D array.
So that's like a tf tidy output property.
Yeah, I think so. Yeah. So it's a tensor. So by data, you're probably accessing. Here we can look at it, right? Yeah, it's a good question. Let's see how it looks like. So let's reload this. Let's just do 1, 2, 3. Train the network. And predict. I have to actually call predict. Start predicting. Stop predicting. Okay. So So predicted class is what? Looks like an int. And where is that? So we're accessing what? Await predicted class data. So I would imagine I would see a data here, but I don't see a data attribute. Oh, that's a method, not an attribute. Sorry. So maybe I need to plot this and this as well. And let's run it again. I might have to reload it though. Okay. So 0, 1, 2, 3. And start predicting and stop predicting. Okay. So yeah. So it's a method, synchronous method, and probably this is the value here. Value 2. Oops, sorry. 2. So scissors, maybe that's what it's predicting 2.
Yeah, okay. I think that the promise is a JavaScript object that's like the output of an async method, right?
Yeah.
Uh,
So it's fulfilled, yep, and probably this is a value, yeah. Yeah, we're looking at the 0th element, probably, yeah, which is this guy. So this could be 0, 1, or 2. And if it's 0, 1, or 2, we'll classify it as rock, paper, scissors here. Awesome. So that's what happens under the hood here. Let me see. For the exercise, you were supposed to build a more complicated model on this, similar to this with image classification, but you would extend it to, instead of rock, paper, scissors, you would add 2 more classes. And I wanted to show you a clip of where that came from. So this came from this TV show that we've seen in the past, The Big Bang Theory, of adding rock, paper, scissors, lizard Spock. So I'll actually pause the recording here because I'm going to play a screenshot from the actual show. So YouTube has this limitation that we cannot show recorded TV shows there. So I'm going to just for YouTube, I apologize. We'll be back in 1 second. I'm just going to show the episode where this is introduced and what are the rules of this game and which hand beats which hand. So we're just showing how the rock, paper, scissors lizard Spock was introduced in the Big Bang Theory. Yeah. So I went through that exercise. Let me show you some sample data so you have an idea of what that looks like. So the training data is both some natural pictures as well as some computer generated images. Lawrence, has a lot of great examples with generating these computer generated images. So the lizard is this, rock, paper, scissors is the same, and the Spock is this one, which is, I can only do with my right hand. I can not do it with my left hand, which was weird because I had to click as well with my button to capture images. So yeah, I can open that real quick if you want me to. We're not gonna look at the code, but I can show you how that looks like.
So I actually found that to pass the exercise, one of the challenges was you wanted to provide as diverse a training set as possible, right? So I took images of the Spocks and the lizards with the left and right hand, and clicked on the mouse with the opposite hand, and it was
Yeah, not
A
only
bit more contortion than I expected.
it it took me, I think, 2 or 3 efforts to get this right. And I noticed in the notes it said that you should not have anything with sleeves. And in the beginning I had sleeves, maybe that had something to do with it. But then later on I didn't have any sleeves and I captured way more data. I actually ended up beefing up my DNN a little bit because I was getting this I was getting less than 66% accuracy in the test set, which is what the grader expects. But let's do some rock just for fun. Sorry, I misclassified rock, paper, and scissors, and Spock. To get my hand right. Let's say let's get about 10 or 15. And lizard is this one. Sorry, to put it in front of my face. Okay, let's train it. Training done.
I remember when we did the same with the teachable machine.
Mhm.
So it worked better when my face was not in the, in the camera.
In the frame,
So
yeah.
yeah, in the frame, right? So if only the hand was in the frame.
Yeah.
Was that rock, paper, scissors as well? I don't recall.
I don't remember which version we showed. I think we discussed this 5 Lizard Spock, but I think it was rock paper scissors.
Yeah. And if I look at these training examples I have here, you see he's kind of hiding his face and he's not wearing any sleeves. I mean, obviously everybody's background is going to be different. Like mine has a lot of things in the background, so definitely that's playing a role. But let's see, start predicting. So rock. Ooh, I didn't get a lot of paper. Good data, I guess. Scissors gets it right. Paper didn't get it right. Spock gets it right. Lizard gets it right, but not paper. Okay. Maybe I capture paper with my face in it. When I hide my face, it thinks it's something else. Cool. Stop predicting, and this download model downloads that JSON file as well as the weights, the .bin weights, and that's what you're supposed to submit for the exercise. Find this interesting, very interesting. Cool. So this was week 4. I was planning on building a guinea pig classifier, but I didn't have the time. And plus, it's so hard to capture data with that. My goal was to build a qubit and a butters classifier. So maybe next time. They're very hard to capture data with. Cool. I'll stop sharing here and let if you have any questions. Otherwise, I'll hand it over to Robert.
Not sure if it was a question. I guess David did mention something about the webcam one line may not be necessary for certain systems.
Yeah, so in the init function on the script.js, I think it is, George, or no, index.js. Can you look at that real quick? The init function called predict on the model with the webcam. The very bottom of the files. That tidy, see where it calls mobile.predict?
Mm-hmm.
And the only thing I think of is maybe that's to turn on the webcam or something. I mean, I already have my webcam on, so I ran it without that line and it works just as well. So I haven't turned off my camera and tried it, but I wonder if that's I wondered, it's not used for training. It's not, why do they call it capture?
I remember. Lawrence might have mentioned this. I forgot. I think he mentioned that based on the device you're running, maybe you don't have a lot of RAM, or maybe you don't have a high-end device, but basically it might take a little bit of time for your Mobilenet to load as well as your camera to turn on. So I think he used this line to basically turn on the camera and just warm it up, what he mentioned. Like basically just give the system a little of time to read something from the camera and load Mobilenet before you start doing any data capture or prediction.
Right. Well, it's in a sync function, but yeah, it could take a while, right? So yeah, I thought so. Maybe it is turning on the camera. is why it pops up.
Yeah. This Mobilenet predict, I think, is just an empty run, like a first run, so that Mobilenet also takes some time to load and do the first prediction. But after that, I think it takes significantly less time.
Okay.
Yeah, that's just part of it. It never happens again. And then after that, there's training or predict. And the predict does the same, right? Captures, does the Mobilenet prediction, and then uses our model, the DNN, and returns the class.
Yeah, so it's almost like initializing the hardware. It's not really
Yeah, exactly. That's what he mentioned in the class, if I remember correctly.
cool.
And you have a TF data link as well. Okay. Take a look at that. Awesome.
All right, thank you, George and David, for walking us through weeks 3 and 4 of this TensorFlow data and deployment course, browser-based models, and wrapping that up. As we mentioned at the beginning, but I'll just do a brief reminder here for folks that have joined in the interim. Share my screen over here. Next week, we will commence talking about the second course in this TensorFlow Data and Deployment Specialization, device-based models with TensorFlow Lite. So that'll be next week at 7 p.m. Eastern, again on Deep Learning Adventures. And this course, there'll be 4 weeks worth of material in the course. We'll try to finish it in 2 weeks. We'll see if we succeed at that. First course, device-based models with first week. Device-based models with TensorFlow Lite. Talks about a lot of the items that are needed in order to move models from the cloud, from your GPUs and laptops to cell phones and embedded devices. And then in the last 3 weeks of the course, there's different use cases. There's an Android app week 2. Then iOS is on week 3, and TensorFlow Lite on devices, where we'll get it onto Raspberry Pi for week 4. So definitely looking forward to that. Hope you all are able to join us. And with that, I guess we'll wrap up tonight's meetup. Thanks again for joining, and hope to see you for future deep learning adventures.
Thank you, friends. This was awesome.
Thank you, guys.
Thank you, George.
Thank you, friends. Appreciate it.